Deep beneath the fractured ice of a moon circling Jupiter, an ocean has been hidden for 4 billion years. There is no sunlight down there, no weather, no surface to look out from, just an enormous body of liquid water wrapped around a rocky seafloor, heated from the inside by the gravitational pull of the largest planet in our solar system. That ocean has been doing things in the dark for a very long time, dissolving rock, building chemistry, pushing traces of itself upward through a ceiling of cracked ice, leaving a record written into the frozen surface above. In 2023, a telescope that had been operational for less than a year pointed at that surface for just a few minutes and read that record. The James Webb Space Telescope detected carbon dioxide, the molecular backbone of every living thing ever found on Earth, concentrated precisely in the regions where Europa's ice had been most recently broken apart and refrozen. Every chemical signal pointed downward, toward the ocean below, an ocean that may hold twice as much liquid water as every sea on Earth combined. Webb didn't discover Europa, it finally saw it for what it actually is. Part 1. The Discovery. In September 2023, two separate scientific teams published their findings on the same day in one of the most respected research journals in the world. Both had used the same telescope. Both had pointed it at the same target. Both analyzed the data independently, and both arrived at the same conclusion. The James Webb Space Telescope had detected carbon dioxide on the surface of Europa, the ice-covered moon of Jupiter. And the distribution of that carbon dioxide was not what anyone would expect if it had simply drifted in from space. It was concentrated in one specific area, a geologically young and disrupted region called Tara Regio. The chemical form it was found in, and its tight relationship with the terrain directly beneath it, all pointed toward a single origin, the ocean below. Not an ocean anyone has directly seen, not one confirmed by any probe, drill, or camera. An ocean that science had been reconstructing for decades using gravitational data, magnetic measurements, and surface geology. And now, for the first time, from chemical evidence. Something carbon-bearing had traveled upward through kilometers of ice and left its mark on the frozen surface of a moon more than 600 million kilometers from Earth. Webb did not find life on Europa. It did not detect movement, biological structure, or signals of any kind. What it found was arguably more consequential, evidence that the chemistry of a hidden ocean is leaking upward through the ice, concentrating in the places where the crust has been most recently broken and refrozen, and that this leakage carries carbon-4, one of the 6 chemical elements that every known form of life depends on. That is what seeing Europa for the first time actually means. It does not mean humanity had never noticed Europa before. Galileo Galilei spotted it in 1610 when he turned a primitive telescope toward Jupiter and counted 4 points of light circling the planet. Europa appeared in textbooks, scientific proposals, and science fiction for the 4 centuries that followed. What first time means here is something narrower. For the first time, an instrument with the spectral resolution of Webb examined Europa's surface chemistry at a level no previous telescope could approach, and returned a chemical fingerprint that tightens the connection between the icy surface we can see and the liquid ocean we cannot, in a way that makes the entire system feel less like a theory and more like a real, active place. Part 2. How Webb reads a world. To understand why this matters so much, you need to understand what Webb actually did. The James Webb Space Telescope sits approximately 1.5 million kilometers from Earth at a gravitational balance point called the second Lagrange point. From there, it looks outward with instruments tuned to infrared light, wavelengths just beyond what human eyes can detect. Infrared is the language of molecular vibration, of chemistry read across enormous distances. When infrared light falls on a surface, different molecules absorb and reflect it at different wavelengths. Carbon dioxide absorbs infrared at a specific set of wavelengths. Water ice absorbs at different ones. Sulfur compounds, salts, and organic molecules each leave their own distinct pattern, a chemical fingerprint encoded in the spectrum. This technique is called spectroscopy, and it is one of the most powerful analytical tools in all of science. It works because every molecule vibrates. The atoms within it stretch, bend, and rotate at frequencies determined by the molecule structure, its mass, and the strength of its bonds. When an infrared photon arrives at a surface and its energy matches the vibrational frequency of a particular bond, the molecule absorbs that photon. That wavelength disappears from the reflected signal. The pattern of missing wavelengths identifies which molecules are present, without touching anything, without collecting a sample, without being anywhere near the surface. Webb's near-infrared spectrograph splits incoming light into thousands of individual wavelength channels, each recording how much light arrived at that precise color. The result is not a photograph. It is a chemical inventory, pixel by pixel, of what molecules sit on the surface of a world more than 600 million kilometers away. From Webb's position, Europa appears as a tiny disk of reflected sunlight embedded in the glare of Jupiter. The infrared photons carrying its chemical information have traveled from the Sun to Jupiter's orbit, reflected off the ice, and traveled all the way back to reach Webb's mirror. By the time those photons arrive, they are extraordinarily faint, a whisper buried inside a roar of background light. Extracting that signal requires Webb's 6.5-meter gold-coated mirror and an instrument capable of isolating that whisper simultaneously by wavelength and spatial position. The observation of Europa took only a few minutes of telescope time. Those minutes produced a data set that two independent teams each spent months working through, and both arrived at findings that fundamentally changed how scientists think about this moon. Part 3. Europa and its hidden ocean. Chaos terrain is a formal geological category describing places on Europa's surface where the icy crust has been broken apart, scrambled into rough and irregular blocks, and refrozen in a disordered configuration. These regions don't look like smooth plains or orderly ridges. They look like a frozen jigsaw puzzle whose pieces were violently displaced and then locked in place by a sudden refreezing, the geological signature of something working on the surface from beneath. That something, in all likelihood, is the ocean. Europa is smaller than most people picture. Its diameter is roughly 3,122 kilometers, making it the smallest of Jupiter's 4 large Galilean moons and only marginally smaller in width than Earth's own moon. From a distance, it appears as a pale marble crisscrossed by faint reddish-brown lines, the kind of world you might assume is frozen solid and geologically dead. That assumption is wrong in almost every important way. Beneath Europa's smooth, reflective surface lies what may be the largest ocean in the entire solar system relative to the body containing it. Estimates place its volume at roughly twice the combined volume of every ocean on Earth. The Pacific, Atlantic, Indian, Arctic, and Southern combined, doubled, contained inside a moon that could fit inside the continental United States. The ocean is global, encircling the entire moon in a continuous shell of liquid water beneath the ice. There are no continents, no coastlines, no exposed surface. It exists in total darkness, sealed beneath a crust of ice tens of kilometers thick, and may extend 60 to 100 kilometers downward before reaching the rocky seafloor. Before 1979, Europa was little more than a moving point of light. Scientists expected it to look like Callisto, Jupiter's outermost large moon, a heavily cratered sphere pockmarked by 4 billion years of accumulated impacts, geologically dead. When Voyager 2 passed through the Jupiter system in July 1979 on a trajectory that brought it close to Europa, the images that came back changed everything. Europa's surface was the smoothest, solid surface of any body yet found in the solar system. Impact craters were almost completely absent. The globe was covered in water ice and crossed by an extraordinary network of ridges and fractures stretching thousands of kilometers across the surface. Europa looked like a frozen ocean whose surface had cracked, shifted, and refrozen repeatedly, continuously erasing old features and replacing them with new ones. The near absence of impact craters was the key diagnostic. On geologically dead worlds, craters accumulate steadily because nothing erases them. Europa's nearly pristine surface meant the ice was geologically young, perhaps only 60 to 90 million years old, which meant something was continuously resurfacing the moon. The most natural explanation was liquid water beneath the crust. Part 4. Confirming the ocean and its engine. Between 1995 and 2003, the Galileo spacecraft orbited Jupiter and made multiple close passes of Europa, studying its magnetic environment. Jupiter has the most powerful magnetic field of any planet in the solar system, roughly 20,000 times stronger than Earth's, rotating with the planet and sweeping its influence past the orbits of Jupiter's moons like a vast lighthouse beam. Any electrically conductive material within range of this rotating field will respond by generating its own secondary induced magnetic field. Galileo's magnetometer team, led by Margaret Kivelson, detected exactly this secondary signature around Europa. Rock is not conductive enough to explain it. Solid ice is an insulator. The only physically consistent explanation was a global ocean of salt water, a brine with enough dissolved ions to carry electrical current strong enough to produce the observed magnetic response. The consensus that formed around that evidence has never seriously wavered since. The question that followed immediately was both simple and profound. How does a moon this small, this far from the sun, maintain a liquid ocean rather than freezing solid? Europa's surface temperature hovers around -160 degrees Celsius. Under ordinary circumstances, a body this cold at this distance from its star should be frozen through to its center. The answer has nothing to do with sunlight. It has everything to do with gravity. Europa's orbit is slightly elliptical, maintained by a gravitational relationship with two neighboring moons, Io and Ganymede. The three moons are locked in a Laplace resonance. For every orbit Ganymede completes around Jupiter, Europa completes exactly 2, and Io exactly 4. This prevents Europa's orbit from gradually circularizing over time. As Europa moves along its elliptical path, its distance from Jupiter changes continuously. When it swings closer, Jupiter's pull is stronger. When it moves farther, the pull weakens. This rhythmic variation physically flexes Europa's entire body with each orbit, stretching and compressing it slightly, like a rubber ball squeezed and released over and over. Flexing generates friction. Friction generates heat. This process, tidal heating, is the engine that keeps the ocean liquid. As long as the orbital resonance persists, and it has persisted for billions of years, the tidal engine keeps running. Part 5. The ice shell and its fractures. The thickness of Europa's ice shell became one of the most important open questions in planetary science because thickness determines how easily material can move between the surface and the ocean below. A thin shell, perhaps 5 to 10 kilometers, would allow more direct exchange. Cracks could potentially reach all the way through. Warm water might occasionally breach the surface. A thicker shell, 20 to 40 kilometers, would make exchange more difficult but not impossible, requiring slow internal convection within the ice to transport material upward over geological timescales. Estimates ranged widely for decades. Then, in 2022, NASA's Juno spacecraft made a close flyby of Europa and turned its microwave radiometer toward the surface. By analyzing how microwaves pass through and scattered within the shell, the Juno team estimated its thickness at approximately 29 kilometers, a result published in late 2025. That number was significant, but something else in the data mattered more than the raw thickness measurement. The ice is not pristine. Fractures, pores, and other structural irregularities extend hundreds of meters below the surface. The shell is not a smooth, sealed, monolithic barrier. It is fractured ice sitting over a liquid ocean, and those fractures reach deep. The Juno microwave instrument does not photograph individual cracks. It detects scattering, the disruption of microwave signals as they pass through material that is not uniform. Something within the upper hundreds of meters of the ice shell is interrupting those signals in ways that smooth, solid ice would not produce. The most plausible explanations involve structural complexity within the shell, microfractures too small to resolve from orbit but numerous enough to affect how radiation propagates through the ice, pockets of brine held in a near-liquid state because dissolved salts depress the freezing point of water, and voids created by thermal stress as the shell flexes with every tidal cycle. Their presence changes what the ice shell fundamentally is. A shell with internal fractures, brine inclusions, and microscale porous regions is not a simple slab of frozen water. It is a mechanically complex medium through which dissolved chemicals and trapped fluids can migrate without requiring a crack to penetrate the entire thickness of the ice. Brine pockets could act as intermediate reservoirs, collecting ocean-derived material that percolates upward through warmer, softer ice near the shell's base, holding it at shallower depths where geological disruption can bring it the remaining distance to the exterior. If the ice shell were a perfect, unbroken slab of solid water ice, there would be little reason to expect ocean-derived material at the surface. But a shell that is fractured internally, that slowly convects warm material upward, and that periodically has sections broken apart and refrozen in regions like Tara Regio, that kind of shell is permeable enough that over thousands to millions of years, molecules from the ocean can work their way up and leave detectable traces on the exterior. Chaos terrain is the surface evidence that this permeability is real. Part 6. Tara Regio. When you examine Europa's surface in detail, the chaos regions stand out immediately. Patches where the normal pattern of ridges and smooth plains has been dramatically disrupted. Blocks of ice appear to have broken free, rotated, and then locked in place as the surface refroze, like ice flows on a river beginning to thaw, frozen mid-motion. The leading explanation involves warm material rising from below. Heat from the ocean or from a pocket of warm water within the ice shell thins and weakens the overlying crust until it fractures. Ice blocks shift during the disruption event and then become permanently fixed as fresh ice forms around them. The result is the rough, jumbled terrain that characterizes every chaos region on the Moon. Tara Regio is one of the most extensive chaos regions on Europa. It spans approximately 1,800 kilometers and sits on the Moon's leading hemisphere, the side that faces forward in the direction of Europa's orbital motion. What makes it especially significant is not only its geological youth but its chemical distinctiveness from surrounding terrain. Before Webb, the Hubble Space Telescope had detected evidence of sodium chloride, ordinary table salt, concentrated in Tara Regio. On Earth, sodium chloride dissolves readily in ocean water and is one of the primary minerals in seawater. Finding it concentrated on Europa's surface in a region of disrupted ice strongly suggested that salty water from the ocean below had reached the surface and left its dissolved minerals behind. Webb's carbon dioxide detection added a second chemical data point to the same location. First salt, now carbon, both concentrated in the same terrain, both chemically consistent with an origin in the ocean, both deposited in the region, showing the clearest geological evidence of ocean surface exchange. The accumulation of chemical evidence in Tara Regio transforms it from an interesting geological feature into something more like a natural reading station, a location where ongoing ocean surface interaction has been writing a legible chemical record that instruments are now sophisticated enough to read from hundreds of millions of kilometers away. Part 7. Habitability and carbon. Habitability does not mean a place is inhabited. It means the conditions necessary for life, as understood from every example of life ever found, are present and in principle accessible. Every environment on Earth where life has been discovered shares three characteristics: liquid water, a source of usable chemical energy, and the right chemical elements in accessible forms. Europa has been evaluated against this checklist for years. Liquid water was effectively confirmed by the Galileo magnetometer data in the late 1990s. Chemical energy became plausible once researchers recognized that Jupiter's radiation continuously manufactures oxidizing compounds on Europa's surface. Compounds that could, if transported into the ocean, react with reduced compounds from the seafloor to release energy. Hydrogen, oxygen, and sulfur compounds were all accounted for. Phosphorus has not been directly identified, but models of water-rock interaction predict it should leach from silicate minerals on the seafloor over geological timescales. Carbon was the critical remaining gap, not because scientists doubted it was present, but because no previous instrument had the spatial resolution to determine where carbon-bearing molecules actually came from. Webb settled that question. The most physically plausible source is the rocky seafloor. Europa's silicate mantle contains carbon locked in mineral structures and organic compounds from the primordial material that built the solar system. When ocean water contacts this rock near regions of elevated heat, chemical reactions dissolve minerals and release their constituent elements. One important pathway involves the interaction of water with iron and magnesium-bearing silicates. At elevated temperatures, these reactions produce molecular hydrogen as a byproduct, a process called serpentinization, along with conditions favorable for forming simple carbon-bearing molecules including methane and carbon dioxide. None of these reactions require biology. They require only rock, liquid water, heat, and time. Europa has had all four for potentially 4 billion years. That is what Webb detected the surface expression of: carbon liberated by water-rock chemistry at the seafloor, dissolved into ocean water, carried upward by convection, transported through fractures and brine inclusions within the ice shell, and deposited on the surface in chaos terrain where the crust was most recently disrupted. There is also a second layer of chemistry working in the opposite direction. Europa's surface is bombarded by intense radiation from Jupiter's magnetosphere, which breaks apart water molecules and produces oxidizing compounds, a process called radiolysis. On Earth, ecosystems at deep-sea hydrothermal vents sustain themselves on the reaction between oxidants in the surrounding water and reductants rising from the vents below. No photosynthesis, no sunlight, just chemistry. Europa may offer an analogous setup, with radiation manufacturing oxidants at the surface, and those oxidants potentially transported downward through the fractured ice toward reduced compounds rising from the seafloor. Whether that downward transport occurs at rates high enough to matter is a question no telescope can answer from this distance. Part 8. The seafloor and the ocean. Europa's water layer rests on a rocky silicate mantle, and the contact between the ocean and the rock below forms a seafloor that may be one of the most scientifically important geological boundaries in the solar system. On Earth, the interaction between ocean water and hot rock at mid-ocean ridges produces hydrothermal vents, fissures through which superheated, mineral-saturated water erupts into the cold ocean above. These vents create sharp chemical gradients that sustain entire biological communities independent of sunlight. Tube worms, heat-adapted bacteria, blind shrimp, complex ecosystems drawing entirely on the chemistry of water and rock. A study published in 2021 proposed that Europa's seafloor should be hot enough, given the tidal energy deposited in the moon's interior, to support active volcanic processes. If hydrothermal systems exist there, they would provide exactly the kind of concentrated chemical energy that supports deep-sea life on Earth. Whether Europa's seafloor is actually volcanically active remains unconfirmed. Some models suggest sufficient tidal heat for active eruptions. Others describe a more passive scenario where water percolates through porous rock without dramatic venting. Both are consistent with the chemical evidence Webb detected at the surface. If the liquid layer extends 60 to 100 kilometers below the ice, the pressure at the seafloor would be substantial, though Europa's gravity, about 1/7 of Earth's, reduces the pressure generated by each kilometer of overlying water. Life on Earth exists at the pressures found at the bottom of the Mariana Trench, and there is no known physical or biological principle that would categorically exclude life at Europa's even greater depths. The temperature gradient from a cold ice base to a warm rocky bottom would drive convective circulation throughout the entire water column. Warm water rising, cooler water descending, redistributing heat, dissolved chemicals, and nutrients throughout a body of water that may extend more than 60 kilometers from top to bottom and has been operating continuously for billions of years. Part 9. Enceladus as a comparison. Saturn's moon. Enceladus is the only body beyond Earth whose subsurface ocean material has been directly sampled. NASA's Cassini spacecraft flew repeatedly through plumes of water vapor erupting from vents near Enceladus's south pole between 2005 and 2017, building a chemical portrait of the ocean below that no remote telescope could have produced. The plumes contained sodium chloride and sodium bicarbonate, salts indicating prolonged contact between ocean water and rock. They contain silica nanoparticles that on Earth form only in hydrothermal systems above roughly 90 degrees Celsius, implying active venting on Enceladus's seafloor. And critically, they contained molecular hydrogen, the byproduct of serpentinization, and the same chemical fuel that sustains microbial communities at hydrothermal vents on Earth. Enceladus builds a compelling case for the habitability of ocean worlds, but it is tiny, roughly 500 kilometers in diameter, with a far more modest ocean and significantly less tidal energy than Europa. Europa's ocean is vastly larger, almost certainly older, and potentially far more chemically complex given the greater scale of water-rock interaction across a much more extensive seafloor. Where Cassini gave scientists a direct chemical sample through plume sampling, Webb is providing something different and complementary, a spatially resolved chemical map of where ocean-derived material reaches Europa's surface, tied to specific geological features with their own independent explanation for why the material arrived there. Together, these two moons are building an argument that extends beyond what either demonstrates alone. Ocean worlds in the outer solar system are not isolated anomalies. They appear, at least twice, to be chemically active environments where the basic ingredients for habitability are measurably present, even from vast distances. Part 10. Europa Clipper. On October 14, 2024, A SpaceX Falcon Heavy rocket lifted off from Kennedy Space Center carrying the largest spacecraft NASA has ever built for a planetary science mission. Europa Clipper, a solar-powered orbiter spanning more than 30 meters with its arrays deployed, roughly the length of a basketball court, began a journey of approximately 2.9 billion kilometers toward Jupiter. It completed a gravity assist flyby of Mars in March 2025, will swing past Earth in December 2026, and is scheduled to enter orbit around Jupiter in April 2030. Once there, it will not orbit Europa directly. Jupiter's radiation is too intense for a spacecraft to survive prolonged exposure at Europa's orbital distance. Instead, Europa Clipper will orbit Jupiter on wide, looping trajectories that carry it in and out of the radiation zone, performing 49 close flybys of Europa over its primary mission. Some passes will bring the spacecraft within 25 kilometers of the surface, close enough to study the ice in detail that no telescope from hundreds of millions of kilometers away could match. The spacecraft carries 9 scientific instruments. An ice-penetrating radar will send radio waves through the shell and listen for reflections from subsurface boundaries, potentially detecting liquid water pockets or the ocean ice interface directly. A thermal camera will map surface temperatures at high resolution, searching for warm regions that could indicate recent geological activity. A mapping spectrometer will characterize surface chemistry at scales hundreds of times finer than Webb can achieve. A mass spectrometer will analyze particles sputtered from the surface by radiation, or if active plumes are present during a flyby, sample water vapor and ice grains ejected from the interior. Webb's observations are already shaping how this mission will be conducted. The chemical map Webb assembled gives the mission team a scientifically grounded guide, where carbon dioxide concentrates, where chaos terrain correlates with elevated volatile content, where ice texture suggests recent disruption. When Europa Clipper sweeps past Tara Regio, it will do so already knowing that Webb detected ocean-sourced carbon there. The radar will probe the ice structure beneath that region. The spectrometer will examine the surface chemistry at resolutions far beyond what Webb could achieve. This is a targeted investigation built on chemical evidence that did not exist before September 2023. Europa Clipper will not arrive alone. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023 and is expected to arrive at Jupiter in July 2031. JUICE will study Jupiter and 3 of its large moons, with primary focus on Ganymede, but will perform 2 close flybys of Europa, providing complementary data from different orbital geometries and at different points in time. Between these 2 missions, scientists will assemble the most comprehensive observational data set ever built for any ocean world beyond Earth. Part 11. What we have done from a distance. Even before either spacecraft arrives, everything described here was gathered by instruments that never touched Europa. Webb sits 1.5 million kilometers from Earth, pointed at a moon more than 600 million kilometers away. Galileo flew past Europa, but was crippled by an antenna failure. Hubble observed from Earth orbit. Juno took microwave measurements during a single brief flyby of a moon that was not its primary target. And yet, from all of this, science has assembled a specific and internally consistent portrait of an alien ocean world, specific enough to place carbon dioxide on a geological map, connect it to a particular type of terrain, identify that terrain as the surface expression of ocean surface exchange, and trace the carbon's likely origin through a chain of processes extending from the rocky seafloor all the way to the ice above. We have never touched the surface. We have never sampled the water. And yet we can describe where the ocean's carbon appears on the exterior, what form it takes, how recently it was deposited, and which processes most likely carried it there. Even Europa Clipper and JUICE, with all their combined capability, will not be positioned to answer the deepest question this inquiry keeps returning to. Is anything alive down there? Answering that with confidence would require landing on the surface, drilling through the ice, or sampling plume material with instruments designed to detect biosignatures at the molecular level. No such mission currently exists beyond concept studies. But even without that final answer, the evidence already in hand changes the scientific standing of Europa in a fundamental way. It is no longer a distant candidate filed away under maybe. It is a world with a demonstrated chemical connection between its surface and its ocean, where carbon from the ocean reaches the frozen exterior precisely in the places where the crust has been most recently disrupted, and where the conditions for habitability are not theoretical possibilities but observationally constrained parameters measured with real instruments against a real world. Closing Europa has been there for 4 billion years. Its ocean has been liquid for most of that time, maintained by a tidal engine running continuously since Io, Europa, and Ganymede first locked into their gravitational resonance around Jupiter in the early history of the solar system. Whatever is happening beneath that ice has been happening in total darkness and silence for longer than life has existed anywhere on Earth. We are not discovering Europa. We are catching up to it. The ocean was there before humanity had telescopes capable of resolving the disk of a distant moon. The carbon was cycling through the water and working its way upward through the ice before anyone had spectrographs sensitive enough to detect a specific molecule from hundreds of millions of kilometers away. The chaos terrain was forming and refreezing before any human eye looked up at Jupiter and seriously wondered what those tiny points of light might be concealing. What Webb did was not uncover a secret place there waiting to be found. It made visible something that had already been happening for an incomprehensibly long time, in a place where no observer had ever been present. The ice cracked. The ocean pushed its dissolved chemistry upward through the shell. The carbon arrived at the surface and settled into the terrain shaped by the same process that delivered it. And in 2023, a telescope that had been in space for less than a year pointed its infrared spectrograph at that surface for a few minutes and read the record that billions of years of ocean surface exchange had been quietly, continuously writing into the ice, with no audience, no purpose, and no expectation that anything would ever come along to read it. It is not a message. It is not evidence of intention. It is simply matter doing what matter does in the presence of water, heat, and time. Chemistry operating in the dark on a world that has never been waiting for us, and we are only just beginning to read it.